Hello and welcome to this session in which we will consider another problem on the transients of the first law of thermodynamics. In this particular problem, we have been given that we have a 1 meter cube tank of ammonia So, the initial state is given as 150 kPa and 25 degrees Celsius. The tank is attached to a line in which ammonia is flowing. Let us put a valve over here. Okay. So, the line pressure is given as 1200 kPa at 60 degrees Celsius. So, ammonia flows from the line to the tank because the pressure in the line exceeds that of the tank. Once the valve is opened, mass flows into the tank until half of the tank is filled with ammonia, with liquid ammonia. So, at state 2, volume of liquid is equal to 0.5 meter cube because the whole tank is 1 meter cube, and volume of the vapor or Vg, let us use the subscripts Vf for the liquid fluid and Vg for the vapor gas, is also 0.5 meter cube, and both these states are at equilibrium at 25 degrees Celsius. So, we have to find out the heat transfer from the tank during the process. Okay. Let us first write down the conservation of mass. So, obviously M2 minus M1 is equal to Mi minus Me is still valid, but here there is no exit, thus Me vanishes. So, this is the conservation of mass. These are all the states. So, the second thing is to write down the conservation of energy. So, M2U2 minus M1U1 is equal to Q minus W plus Mi Hi minus Me He. So, given that there is no exit, so this term vanishes, and also given there is no work done by the system or on the system, the work done vanishes. So, you simply have Mi Hi, M2U2, M1U1 and Q, where we have implicitly neglected the total contributions from the kinetic energy and the potential energy towards the internal energy and the enthalpy. So, thus, we have simply written U2 total as U2, U1 total as U1, Hi total as Hi. Okay, there we go. So, given that we know exactly what state 1 is, we know U1 and M1 because we will know what the specific volume corresponding to this state for ammonia is, and given that we know the total volume, we will know the total mass. At state 2, we have the volumes of the two fluids, okay, and if we know the volumes of the two fluids, we can find out the quality, because if we have the dome like this, we know the specific volume at 25 degrees Celsius. This is the isotherm, 25 degrees Celsius. So, at 25 degrees Celsius, we know the specific volume of pure vapor and of pure liquid, and if we know that, we can know using the specific volume and the total volume, the total masses of the vapor and the liquid. So, if we know the total mass, we can then find out x. So, given this information, we can find out what state 2 corresponds to exactly, and thus we can know what U2 is, and given the volumes and the specific volumes, we will know what M2 is also. So, M2, M1, U2, U1 are known, M2 is known, M1 is known. So, Mi will be found out using this equation. If Mi is known and Hi is also known, because we know the inlet conditions for ammonia, which is 1200 kPa at 60 degrees Celsius. So, even this will be known, and using all this information, the Q will also be found out eventually. So, let us start plugging in these values. So, we have M2 equal to M2 minus M1 is equal to Mi, we have M2 into U2 minus M1 into U1 is equal to Q plus Mi into Hi, where U1 is equal to internal energy of ammonia T equal to 25 and P equal to 150. Then we have U2 equal to int energy ammonia at T equal to 25, but X equal to X2. Let us find out what X2 is. So, X2 is mass of vapor at 2 divided by the total mass, where mg2 is equal to 0.5, which is the volume, by the specific volume of ammonia at T equal to 25 and X equal to 1. Similarly, m fluid 2 is equal to 0.5 by the volume, the specific volume of ammonia T equal to 25, X equal to 0. Here I have made use simply of the fact that if X equal to mg by mg plus mf, then I must know what mg is. So, mg is equal to the volume of the vapor occupied by the specific volume. So, this is the volume of the vapor which is there in the total container, and this is the specific volume. This is how we find this out. So, this is for the vapor, this is for the fluid. Okay. X equal to 0 implies fluid, the quality X equal to 0 is for fluid. So, this is how you find out X2. Alright. So, we know U1, U2, and we also know the masses of the vapors and liquids. So, M2 is simply Mg2 plus Mf2, okay. And mass of the initial condition is simply 1 by volume of ammonia T equal to 25 and P equal to 150. This is because the initial condition is this, and initially there is 1 meter cube of ammonia, and so the initial mass M1 is equal to the initial volume or the volume, which is simply 1 meter cube by the initial specific volume. So, this is equal to 1 by the specific volume at the initial condition. So, this is 1 divided by the specific volume at the initial condition, which is 25 degrees Celsius and 150 kPa. So, we have M1, we have M2, and we have all the energies except the enthalpy at the inlet line. So, Hi is equal to the enthalpy for ammonia. So, what is the inlet condition? Let us find out. It is 1200 kilopascal at 60 degrees Celsius. There you go. So, let us solve this. And so, the amount of heat transferred from the system, we obtain Q as minus 379,518 kilojoule. That is a huge amount of heat transfer. And so, this heat, the sign indicates its heat transfer from the system to the surrounding. So, if someone asks what is the heat lost, then you will say the heat transferred from the tank is 379.51 megajoule. Okay. So, when if you want to go very scientific, you will say the heat transfer to the system is minus 379518 kilojoule. So, with the help of conservation of mass and conservation of energy, we were able to solve this problem. And the slightly interesting thing was finding out the X using the fact that the final state was given as half volume of liquid. So, the solution says actually the X was 0.01279. Okay. So, I hope you will work this problem out on your own. You will try to work out all the logic behind the problem, and you will be able to solve many more problems of this kind on your own. So, with this we end this session, and I will see you next time. Thank you.